You ever look at a complex machine, like a car engine or a big factory robot, and just wonder, how does it all work? It looks so complicated, right? But what if I told you it's all built from a really simple set of rules, almost like a secret language of motion? Well, let's dive in and see if we can decode that language together.
Okay, so check this out. You've got one simple motion, just the turn of a handle. But that single input gets transformed by this mechanism into something totally different and way more complex. And that's the whole game right there, taking one kind of movement and predictably turning it into another. It's not magic, it's just really, really clever engineering.
So that brings us to the big question for this explainer. How do engineers do it? How do they design machines that can do literally anything, from digging a ditch to building a smartphone, all starting from something as basic as a spinning motor? How do they translate that one simple rotation into any motion they could possibly dream up?
To figure that out, we have to learn the language. And just like any language you've ever learned, it all starts with the alphabet, the most basic, fundamental building blocks. Once we get the letters down, we can start putting them together to make words and then sentences. So the very first letter in our alphabet of motion is something called a kinematic link. Basically, it's just any single solid part in a machine that's there to transfer force or motion. The best way to think about it is like a single Lego brick. It could be a crank, a lever, a piston, even something flexible like a fan belt counts. It's our absolute most basic piece.
And just like letters in the alphabet, these links come in different shapes. A simple one with two spots to connect to things, we call that a binary link. But you can also have ternary links with 3 connection points or even quaternary ones with 4. And it's these more complex shapes that let us build much more intricate machines down the line.
Okay, so if the links are our letters, then kinematic pairs are the grammar. A pair is just the joint that connects 2 links together. But here's the crucial part. The joint constrains the motion. It forces the 2 links to move relative to each other in a very specific way. Think about a hinge on a door. It only lets the door swing. It can't move up or down. That control is everything. So we've got our letters, the links, and our grammar, the pairs. When we start connecting them all together, we create what are called kinematic chains. But here's where it gets interesting. Just because you built a chain doesn't mean it's useful. Its behavior all comes down to one really important idea. It's freedom of movement.
And that idea is called degree of freedom, or DOF for short. Now I know, that sounds super technical, but trust me, the concept is dead simple. It's basically just a quick way to count and figure out if you've built a machine that's going to move predictably, a structure that's locked solid, or, well, just a floppy, useless pile of parts.
This table here lays it out perfectly. If your chain has 0 degrees of freedom, guess what? It doesn't move at all. You built a structure, like a bridge truss. Super strong, great for a building, but not a machine. On the other end, if you've got more than 1 degree of freedom, it's a wobbly mess, totally unpredictable. The magic number, the absolute sweet spot for almost every machine you can think of, is exactly 1 degree of freedom. That gives you a mechanism where one input gives you one single, predictable output.
Okay, so now that we have the absolute basics down, let's look at one of the most common and most important phrases, or sentences, in this entire language of motion. It's the simple but incredibly powerful 4-bar mechanism.
And this is it. It looks simple because it is just 4 links connected by 4 joints. So link 1, that's our frame. It's bolted down, it's not going anywhere. Link 2 is our input, what we call the crank. When we turn that crank, it pushes on link 3, the coupler, which then drives link 4, our output. It's simple, it's elegant, and it's the foundation for a staggering number of machines.
But just by looking at the parts, how do we know how it's going to move? Is that input crank going to be able to spin all the way around, or will it just rock back and forth? Luckily for us, engineers have a kind of secret recipe they use to predict exactly what's going to happen without ever having to build a thing.
It's called Grashov's Law. And again, don't let the name intimidate you. It's just a super simple 4-step test. First, you find the shortest and longest links. Then, you add their lengths together. After that, you add up the lengths of the other 2 links. And finally, you just compare those 2 numbers. If the first sum, the short plus the long, is less than or equal to the second one, boom, your mechanism passes the test, which means at least one of those links can spin in a complete circle. And that right there, that is huge. That simple little check is literally the difference between designing an engine part that can spin continuously and creating, say, a windshield wiper that just rocks back and forth. It's an amazingly powerful predictive tool that saves designers a ton of time.
So we've seen how these rules help us design predictable motion. But now we get to what I think is the most mind-blowing part of this language. It's a concept called inversion. And it shows us how the exact same set of parts, the very same phrase, can create wildly different machines just by changing our point of view.
For this, let's look at a single slider crank. This is the heart of pretty much every car engine out there. You've got a crank, a connecting rod, and a piston sliding in a cylinder. Now in this case, we fix the cylinder. We bolt it down so it can't move. As the crank spins around, it pushes that piston back and forth, back and forth. We're turning rotation into straight line motion. Classic engine stuff.
Okay, but now watch this. We take the exact same parts, no new pieces, same crank, same rod, same slider. But this time, instead of fixing the cylinder, we're going to hold the connecting rod still. And just like that, the entire mechanism behaves in a completely different way. The crank and the slider now produce this big, sweeping, oscillating motion, which is perfect for certain kinds of machine tools.
I mean, just let that sink in for a second. One set of parts, two totally different motions, two completely different machines. The only thing we changed was which part we decided to hold still, which part we called our frame of reference. That, right there, is the real power you get when you understand the secret language of motion.
And what's so cool is that once you learn to see the links, the pairs, and the chains, you start seeing them everywhere, in your car's suspension, in a pair of scissors, in heavy construction equipment. So now that you know the basic alphabet and grammar, I've got a question for you. What hidden mechanisms are you going to be able to spot in the world around you? I bet you'll be surprised.